Hello everyone, I welcome you all to this 12th lecture of Structure of Atom. Myself Varad Daoo, I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in the last class, what we have seen about the Heisenberg's uncertainty principle, which tells us about that. Uh, First, we studied about de Broglie wavelength, and then we studied the Heisenberg uncertainty principle. So de Broglie wavelength states that each particle has a wavelength characteristic wavelength associated with it, and the wave behavior of matter becomes dominant at the subatomic level, whereas at the microscopic level, the particle nature of matter becomes dominant over its wave nature. Right. Then further we studied about the Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle states that it is not possible to measure simultaneously both the position and momenta of a microscopic particle with an absolute accuracy. Right. So we can, if we measure accurately the position, there will be uncertainty in its momentum and vice versa. And both the things cannot be measured with 100% accuracy, right? And then we also studied about Heisenberg's uncertainty principles, a practical application. Then at the end of the last class, we delved into the quantum mechanics and studied about the quantum mechanical model. We also studied about the Schrodinger's wave equation, right? So let me first try. So we studied about the Schrodinger wave equation, which was del2 psi by del x square plus del2 psi by del y square plus del2 psi by del z square plus 8 pi square ms square into e minus v phi is equal to 0, where phi was called the where phi was the amplitude of the wave, x, y, z are the coordinates of the position of electron, E is the total energy of the electron, V is the potential energy, and M is the mass of the electron, right? And H is the Planck's constant, right? We also studied that this expression could also be written in the form of H psi is equal to E psi, right? Where this stands for the Hamiltonian, that is the operator, right? Hamiltonian operator, right? And we also studied about the significance of Schrodinger wave equation, right? So today we are going to build upon on that. This is lecture 12, structure of atom, right? So first, what we are going to study? We are going to study about the operators. H psi is equal to E psi was there, right? Where this H stands for the Hamiltonian operator, right? So while studying the state of a system, we make various measurements of its position, of its properties, such as mass, volume, momentum, position, and energy. Each individual property is called as observable, right? In order to determine the value of observable property, we have to perform certain mathematical operations, and this operation is represented by an operator, right? Therefore, operator is a mathematical command or instrument or instruction which acts as a mathematical function, right? So an operator is a mathematical command or instruction which acts on a mathematical function. Okay? Like for example, in the equation 4 into 5 is equals to 20. The operator is multiplication, right? The operator is multiplication, right? And the operator is x. The operator is x, right? So we can also express the multiplication operation with some symbol, right? So express the multiplication operation. Multiplication operation as an with some symbols, right? Let's say we designate as m cap, right? So for example, then this 4 into 5 will turn to what? Equal to 20. This operation will turn as m cap of 4 into 5 is equal to 20, right? So in this case, M cap is the multiplication operator, right? Where the cap, this is the cap, signifies operator. So with this understanding, we'll go to the Schrodinger wave equation for hydrogen atom. Schrodinger wave equation for hydrogen atom, right? So the first point of this is when Schrodinger wave equation was solved for hydrogen atom, the solution gives the possible energy states or energy levels that an electron can occupy. These values of energy are called as eigenvalues, and the corresponding values of wave functions, that is psi of the electron associated with these energy values, are called as eigenfunctions. Right? So let us write this down. When Schrodinger wave equation was solved for hydrogen atom, right? The solution gives the possible energy states or energy levels that an electron can occupy, right? And these values are called as eigenvalues, right? The corresponding values of the wave function, on the other hand, the corresponding values of wave function, on the other hand, are called as eigenfunctions, right? The second point of this is the wave functions and the corresponding energy states are characterized by a set of three quantum numbers called as principal quantum number, azimuthal quantum number, and magnetic quantum number. So we are going to study about all these quantum numbers in our subsequent classes. These numbers arise as a natural consequence in the solution of Schrodinger wave equation. This quantum mechanical model of hydrogen atom successfully predicts all aspects of hydrogen atom, all aspects of hydrogen atom spectrum and other phenomena which could not be explained by Bohr model. Right. So what we are saying is let us write this down. The wave function and the corresponding energy states. The wave function and corresponding energy states are characterized by a set of three quantum numbers. Set of three quantum numbers. These quantum numbers are called as principal quantum number, which is denoted by the symbol n. Right? Azimuthal quantum number, azimuthal quantum number, which is denoted by the small l, and magnetic quantum number, which is ml, right? These numbers arise as a natural consequence in the solution of Schrodinger wave equation, right? And this quantum mechanical model of the hydrogen atom successfully predicts all aspects of hydrogen atom spectrum, right? And other phenomena which could not be explained by Bohr model, right? Bohr's model, right? So the third point of this expression is Schrodinger wave equation is the Schrodinger wave equation cannot be solved exactly for multi-electron system, right? However, approximate methods can be used to get the solution of reasonable accuracy, right? So this is the advantages of Schrodinger wave equation. So the third point, let us write down. Schrodinger wave equation cannot be solved exactly for multi-electron atoms. However, approximate methods can be used to get the solution. So let us understand the physical. Next topic which we are going to cover is physical significance of wave function, which is denoted as psi. Right. So in physical sense, psi gives the amplitude of the wave associated with the electron. Right. So we know that in case of light wave, the square of the amplitude of the wave at a point is proportional to the intensity of light. Right. So what is basically psi is psi basically gives the of the wave with electron, right? And the square of the amplitude of wave at that point, right, is proportional to the intensity of light, right? The square of amplitude is proportional to the intensity of light, right? Extending the same concept to the electron wave motion, the square of the wavelength may be taken as intensity of electron at any point, right? Intensity of electron. In other words, psi square determines the probability of finding the moving electron in a particular region, right? That means it gives the probable density. Thus, psi square has been called the probability density and psi as probability amplitude, right? Okay, that means psi square determines the probability of finding the moving electron in a given region, right? That is, it gives the probability density, right? Hence, what we can say is, hence, chi square has been called the probability density, psi as the probability amplitude. Right? Hence, the solution of Schrodinger wave equation replaced the discrete energy levels or orbits proposed by Bohr and led to the concept of most probable regions in space in terms of psi square, right? This is also important. We should write this down. Hence, the solution of Schrodinger wave equation, replace the discrete energy levels or orbits proposed by Bohr and led to the concept of most probable region in spacetime. Most probable region in terms of psi square, right? A large value of psi square means that a high probability of finding the electron at that place, and a small value of psi square means that low probability, right? Higher the psi square, very high, a psi square high means probability of finding an electron is high. If psi square low, then that means that probability of finding an electron is low, right? Therefore, the wave mechanics approach gives meaningful wave functions which describe the position and energy levels of an electron in atom, right? Therefore, the wave mechanics approach gives meaningful wave functions describe the position and energy levels of electrons in an atom, right? Now let us move on to the next topic, which is important features of quantum mechanical model of an atom, right? So important features of the quantum mechanical model of atom, right? The important features of quantum mechanical model are summarized, right? So first is the energy of electron in atom is quantized, that is they can have only certain specific values, right? Which was also the Bohr's model, right? This was also proposed by Bohr's model. The energy of electron in atoms is quantized, that is they can have only certain specific values, right? The second is the existence of quantized electronic energy levels in a discrete discrete results of wave like properties of electron and are allowed the solutions of Schrodinger equation, right? So the existence of quantized electronic energy levels is a direct result of the wave-like properties of electrons are the allowed solution of Schrodinger equation, right? Third point is this gives the most probable region in an atom where the probability of finding the electrons is maximum. Therefore, this model is in accordance with the Heisenberg uncertainty principle and does not specify the exact position and momentum of the electron, but it talks about the most probable region called as orbitals, right? This gives the most probable region in an atom, right? Here's the probability of finding the electrons is maximum, right? Therefore, this model is in accordance with the Heisenberg uncertainty principle, right? And does not specify the exact position and momentum of the electron, right? But it talks about most probable regions called as orbitals, right? The fourth point is an atomic orbital is described with the help of wave function for an electron in an atom. Whenever an electron is described by wave function, we say that the electron occupies that orbital, right? Since many wave functions are possible for an electron, there are many atomic orbitals in an atom. In each orbital, an electron has definite energy. Thus, all the information about the electron in an atom is provided by its orbital wave function, right? An atomic orbital is described with the help of wave function, which is psi, right? For an electron in an atom, right? Right? Whenever the electron is described by wave function, right? Whenever an electron is described by wave function, we say that the electron occupies that. We say that the electron occupies that orbital, right? Since many wave functions are possible, right? Since many wave functions are possible, right? Are possible for an electron. There are many atomic orbitals in an atom. In each orbital, an electron has definite energy, right? In each orbital, an electron has definite energy, right? Thus, all the information about the electron in an atom is provided by its orbital wave function, right? Which is nothing but psi, right? The fifth point is the probability of finding the electron at a point within an atom is proportional to the square of the wave function, right, at that point. Therefore, psi square is also known as probability density and is always positive, right? The fifth point is the probability of finding the electron at a point within an atom is proportional to the is proportional to the square of the wave function. Square of the wave function. Just nothing but psi, mod of psi square, right? At that point, right? Therefore, psi square is also known as probability density and is always positive. The probability of finding the electron in a so 6 point is the probability of finding the electron in a region having a volume dV can be obtained as psi square into dV, where dV is the infinitesimally small volume, right? The probability of finding the electron in a region within in a region having a volume dV can be obtained as psi square into dV, right? Where dV is the infinitesimally small volume which is Tx dy Tz, right? The 7 point is the quantum mechanical model gave three constants known as quantum numbers, which are required to specify the position and energy of an electron in an atom, right? And these we are going to study in the next classes, right? The quantum mechanical model gave three constants known as quantum numbers, right? Which are required to specify the position and energy of the electron, position and energy of the electron in an atom, right? So now what we are going to study, next topic is so we are going to study about orbitals, orbit and orbital, right? The wave characteristics of an atom, of an electron, and uncertainty in its position gave a serious blow to Bohr's model. According to Bohr, the electrons revolve in a well-defined circular orbit, but the idea of uncertainty in position and velocity overruled the Bohr picture of fixed circular orbits. Scientists started looking for a theory which may explain the stability of an atom, the dual character of the atom, and uncertainty principle. So this resulted in a new approach called as wave mechanics in 1927, when Schrodinger described the behavior of electron by a mathematical equation known as Schrodinger wave equation. The solution of wave equation led to the concept of most probable region in a place of well-defined circular path proposed by both. So according to this approach, we cannot simply say that the electron exists at a particular point, but we talk about the certain regions in space around the nucleus where the probability of finding the electron is maximum, and these most probable regions are called as orbitals, right? And thus, an orbital may be defined as a region in the space around the nucleus where the probability of finding the electron is maximum, right? So, let's write this down. So, orbital is the region in space where around the nucleus where probability of finding an electron is maximum, right? If a boundary is drawn, so let us so if a boundary is drawn which encloses a region where there is high probability of finding the electron, right? The figures obtained gives the general picture of an orbital, right? So let us just picture. Let me drag a picture which represents it. So this is a figure, right? So this is a figure, right? So this is the orbital, right? So the color indicates the probability of density. So darker color indicates high probability, and lighter color indicates the less probability. So you can see here this region is a darker one. That means there is a high probability of finding an electron. And as we move away from the center, the probability of finding an electron decreases. And this whole region is called as orbital, whereas only the boundary, right? This will be called as an orbit, right? So electron cloud representation of an orbital. So this is an electron cloud representation of an orbital, where this is an orbit, right? So orbital here is shown by dotted figure representing the electron cloud. The intensity of dot gives the relative probability of finding the electron in that particular region. It may be noted that there are some chances of finding the electron even outside the figure, right? Even outside. However, those are very small, right? So now let us write down the difference between orbit and orbital, right? The next topic is difference between orbit and orbital, right? So just write this down. So this portion we are going to write about orbit, and this portion orbital. This is like this. Okay. The first point is orbit is a well-defined circular path around the nucleus in which an electron revolves, whereas orbital represents the region in a space around the nucleus in which the probability of finding the electron is maximum. Right? So orbit is a well-defined circular path around the nucleus in which an electron revolves, right? Whereas orbital represents the region in space around the nucleus in which the probability of finding the electron is maximum. Second point is it represents the so orbit represents the planar motion of an electron, whereas orbital represents the three-dimensional motion of an electron around the nucleus, right? So it represents the planar motion of an electron, whereas this represents the three-dimensional motion of an electron around the nucleus. The third point is orbit gives a definite path of an electron and this concept is not in accordance with the uncertainty principle, whereas orbital does not specify defined paths, and according to this concept, electron may be anywhere in this region, and this concept is in accordance with the uncertainty principle. Orbit gives a definite path of an electron, and this concept is not in accordance with the uncertainty principle, whereas orbitals does not specify definite path. According to this concept, electrons may be anywhere in this region, right? And this concept is in accordance with the uncertainty principle. So move on to the next point. That is point number 4. So all orbits are circular, whereas orbitals have different shapes, right? For example, S orbital is spherical, whereas P orbital is dumbbell shape, right? So all orbits are circular, whereas orbitals have different shape. The fifth point is orbits do not have a directional constraint or characteristics, whereas except for S orbital, all other orbitals have directional characteristics. Right? Orbits do not have directional characteristics, right? Whereas except S orbital, all other orbitals have directional characteristics. The last point is an orbit can accommodate electrons equal to 2n square, where n represents the principal quantum number, whereas an orbital cannot accommodate more than 2 electrons, right? An orbit, so this we are going to study, can accommodate electrons equal to 2n square, where n represents the principal quantum number, and orbital cannot accommodate more than 2 electrons, right? So these are the differences between an orbit and an orbital, right? So in the next class, so I'll give you a brief introduction. So quantum numbers. So in the next, the next topic is going to be quantum numbers, right? So there are 3 quantum numbers. So these are principal quantum number called as n, right? Then azimuthal quantum number, which is called as L, and the last one is the magnetic quantum number, right? The last one is going to be magnetic quantum number called as ML quantum number, which is called as ML. So the principal quantum number. So this quantum number determines the main energy shell or the level in which electron is present, and it is denoted by n. It can have whole number values starting from 1, such as n equal to 1, 2, 3, 4, and this quantum number also identifies as shell. The shells with n equal to 1 is called as first shell, right? And then n is equal to 2 are called as second shell, and so on and so forth. The principal quantum number also helps in determining the average distance of an electron from the nucleus, right? That is, if n is equal to 1, that is the first shell, it is closest to the nucleus and has the lowest energy. As the value of n increases, the distance of the electron from the nucleus increases, and also the energy of an electron in that shell increases, right? Thus, principal quantum number gives the average distance of the electron from the nucleus, right? Of and energy associated with it, right? So this is the what a new principal quantum number is, and azimuthal quantum number is basically orbital angular momentum is associated with orbital angular momentum, and it is denoted by N. So this is what we are going to study in the next class, and also we are going to study the magnetic quantum number. So in present class, what we have seen about the Schrodinger wave equation. We have seen what is called an operator and an example of operator. Further, we have seen the characteristics or the advantages of quantum mechanical model of an atom over Bohr atom. And then we have seen about the orbital, which is a concept of only this quantum mechanical model, and orbital basically gives the probability of finding an electron and is different from the orbit, okay, which was given by Bohr. So we studied about their similarities and differences, and also we in short studied about the different quantum numbers, right? So in the next class, we are going to study about these quantum numbers, and we are going to delve deeper into it. And further, we are also going to study about the quantum numbers associated with spins, and then we are going to study about Pauli's exclusion principle and Hunt's maximum rule of multiplicity. Right? That is what we are going to study in the next classes. Right? Well, thank you all for attending this class, and I hope to see you again in the next class. Thank you.